Welcome back to the lecture series of network theory. In network theory, there are some theorems which are very useful, and if we apply them to simplify an electric circuits, then we can do that very easily. So it's very important that when we are studying network theory, we should have a good knowledge of those theorems, because frequently there will be need to use them. So in my lecture series, I will cover them one by one. I will start with Thevenin's theorem, which is very important in case of electrical and electronic circuits. This Thevenin's theorem I will cover in 3 classes. The first 2 classes will be based on DC circuits. The first class will be based on DC circuit and independent sources. The second class will be based on DC circuits and dependent sources, and the third class will be based on AC circuits. So let's get started. This theorem states that in any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source, a single voltage source, and a series resistor. That means there will be a single resistor which will be connected in series with that voltage source, where the series resistor, which is represented by RTH, is called Thevenin's equivalent resistance. This is equivalent or internal resistance of the network when looking from the concerned or output terminals with all energy sources deactivated and replaced by their internal resistances. And VTH, which is called Thevenin's voltage, that is open circuit voltage across that concerned or output terminals. I will explain next that what this theorem is all about, and what this RTH and VTH, Thevenin's equivalent resistance and Thevenin's equivalent voltage, they are all about. Now in this circuit you can see that we have multiple resistors and multiple energy sources. Now suppose these two are our concerned terminals A and B, and across these two terminals this load resistor RL is connected. Now when we will suppose find out the current value, how much current is flowing through this resistor, or maybe how much voltage will be dropped across this resistor, then how we can apply that Thevenin's theorem to find out that particular value. So in that case, what we have to do is we have to remove this concerned resistor across which the voltage drop we want to find out, or through which the current value we want to find out. Then for the rest of the network will be represented by a single voltage source, this VTH, and this is called VTH, and this whole network will be represented by again a single resistor RTH, and this VTH and RTH will be connected in series. So other than this RL load resistor, the rest of the part of the network now will be represented by a single voltage source, which is called Thevenin's equivalent voltage, and a single resistor, Thevenin's equivalent resistor or resistance, which are connected in series. Then what we will do next, or in the final stage, we will connect that load resistor again with the network, and then we will find the current value or voltage value, whatever we was expecting. Next we will see that how we can apply Thevenin's theorem in an electrical network, or how we can Thevenize an electrical network to simplify that and to find out whatever is desired. So as you can see here that we have an electrical network which is linear and bilateral in nature. Now here we have multiple resistors, and we have here an energy source which is voltage source. Now suppose we want to find out the current value through this resistor. So these are the terminals that I have marked as AB, and across this AB this RL is connected, and I want to find out what is the current which is flowing through this load resistor by applying Thevenin's theorem. So in the first step, what we have to do is we will remove or will disconnect the RL from the network. So when we will remove this load resistor or concerned resistor, it will create an open terminals between those two terminals. So here now the circuit looks like this after removing this load resistor. Now what we will do in the next step, we will find out the open circuit voltage between or across these two terminals. So after removing this load resistor, whatever now we have in the circuit or in the network, then across these open terminals, we will find out that how much voltage will be dropped, and then that voltage is called open circuit voltage, and that voltage is also called the Thevenin's equivalent voltage, the voltage that finally in the modified circuit, simplified circuit, the voltage source that we will have, VTH, that VTH is this voltage, the voltage that we will be getting here across these open terminals. Now in this step, we will simplify the circuit in such a way that we can find out this open circuit voltage easily. Now for that we may apply KVL, KCL or any other rule or method that we know, but we will apply that method which will be more efficient and which can give us faster solution, or which can save time. Now after finding out this open circuit voltage, what we will do is we will remove the energy sources from that circuit. So if we have a voltage source, and with that voltage, if the voltage source is not ideal in nature, that means with that voltage source, suppose if it has some internal resistance also in that for that voltage source, then we will keep that resistance value in that circuit, and the energy part we will deactivate. But if the voltage source is an ideal voltage source, then we will simply short that path. So here, as you can see in this circuit, between these two terminals, this ideal voltage source was connected in the original circuit. So we have simply shorted that path between these two points or these two terminals. Now if suppose the circuit has any current source, and if that current source is not ideal in nature, that then we will deactivate the energy part, and we will keep the resistance part for that current source. But if the current source is ideal in nature, then we will simply open that path across which the current source was connected in the original circuit. So that is the rule. Now in this step, what we want to do is we want to find out the resistance value or equivalent or internal resistance value when we will be looking from those open terminal. So we will keep our eye here where actually the load resistor or concerned resistor was connected in the original circuit, and through those open terminals we will see the circuit, and we will find out the internal resistance or equivalent resistance of that circuit after deactivating all the energy sources from that circuit. Now when we are looking from this side and we want to get the equivalent resistance of that network, we will start simplifying the circuit from this side, from the opposite side or from the other side. So here if we talk about simplifying this circuit and we want to find out the equivalent resistance, then what we can see here, that if we start solving or simplifying this circuit from this side, then R1 and this R3 we can see they are connected in parallel. So we will simplify accordingly, and then with that equivalent resistance this R2 will be in series. So we will find out the equivalent resistance again between that R2 and this equivalent resistance that we have simplified in the previous step, and then with that equivalent resistance this R4 will be again in parallel. So we will simplify accordingly, and that will be the internal resistance or equivalent resistance across these two terminals of the whole network. So we will in next we will simplify a few numericals where this concept will be more clear. Now after finding out the equivalent resistance or internal resistance, which is called Thevenin's equivalent resistance, what we will do, we will represent the whole circuit other than only RL by a single voltage source, which we have found out as VOC, and this is also, as I said, this is also called Thevenin's equivalent voltage, so VTH, this VOC that we have found out in step 2. So with this voltage source, this equivalent resistance RTH will be connected in series, and this RTH we have calculated in step 4. And then after connecting this VTH and RTH in series between these two terminals, we will connect back the load resistor that we removed in step 1. So this will be RL. Now what we was expecting from this circuit was how much current is flowing through this RL. Now in this simplified circuit we can easily find out that current value, because here in this circuit what we can see that these three components are connected in series. So this equivalent resistance of these two resistors will be RTH plus RL, and the current value will be simply I will be VTH divided by RTH plus RL. So in step 5 what we will do is we will connect this VTH and RTH, and then we will reconnect in the next step RL, and then we will find out the current value. This current is the main current which is supplied by this voltage source VTH in this simplified circuit. But since all these components are connected in series, so current will be same through all of them. So that current is also flowing through this load resistor RL. So this is the way how we Thevenize an electrical network, and we can find out the desired parameter. Next we will apply Thevenin's theorem and we will simplify an electrical network. Now in this network, from what we have to find out is we have to find out the current value which is flowing through this 3 ohm resistor by applying Thevenin's theorem. Now this is the 3 ohm resistor through which we have to find out the current value. So what we have learned is that in the first step we will remove that concerned resistor or load resistor. So this is our terminals across which this load resistor is connected. So first we will remove or disconnect that load resistor or concerned resistor. So now the modified circuit will look like this. It will create an open terminal here. Now in the next step, in step 2, what we have learned is to find out the open circuit voltage across those two concerned terminals. Now in this circuit what we can see here that across these two terminals, here the voltage source having value 6 volt is connected, and on the left side here we have two resistors and a current source. Now since this voltage source is also connected across these two terminals, so the open circuit voltage or the voltage between these two terminals will be the value of this voltage source only. So easily we can find out the open circuit voltage here after removing the concerned resistor. So VOC, the open circuit voltage, or VTH, Thevenin's equivalent voltage, will be simply 6 volt. We don't have to do any more calculation to find out this value for this particular circuit. Now in the next step what we have to do, we have to find out the equivalent resistance of that network, and for that what we have to do, we have to deactivate all the energy sources and we have to keep their internal resistance if they have any. Otherwise for voltage source we will short that path simply, and for the current source we will open that path. And if we go by that concept, then the circuit will look like this. So these are the terminals where the load resistor was connected in the original circuit, and then after finding out the value of VOC, which we have obtained as 6 volt, we have deactivated the energy sources. And in this circuit all the energy sources were ideal, so this 6 volt has been shorted simply, and this 4 ampere current source, this was removed, and it has created this open terminals. Now in this circuit what we can see is we have two resistors, and these are the two concerned terminals. So we will look into that circuit from this side. So we will keep our eye here and we will look into the circuit from this side, and so we will start simplifying the circuit to find out the internal resistance from this side. Now when if we simplify this circuit from this side, and this is our reference terminal, so we can see between these two terminals, this 2 ohm and this 2 ohm, they are connected in series. So simply the RTH value, the internal resistance value for that circuit will be, they are connected in series, so 2 plus 2, 4 ohm. So easily we have found out the VTH value and RTH value. Now in the next step what we will do, in the final step, we will represent the whole circuit by this voltage source VTH, and in series with that the RTH. So this much is the circuit that we had in the original circuit after removing this load resistor. So for this whole circuit, this is the equivalent circuit, VTH and RTH, and they are connected in series. VTH has value 6 volt and RTH has value 4 ohm. Now what we will do, we will reconnect the load resistor that we had in the original circuit and we removed in the step 1. So we will reconnect that load resistor, and through that we want to find out the current, and this value was 3 ohm. So now simply the current that this voltage source VTH will supply, the same current will be flowing through this 3 ohm resistor, and that value is I will be equal to VTH, which is 6 volt, divided by these two are connected in series, and in the final equivalent circuit of Thevenin, by applying the Thevenin's theorem, these three components will be always connected in series. So this RTH and this RL, they will be always connected in series. So for this case it will be 4 plus 3, so it will be 6 by 7. So this will be 0.857 ampere. Now we will solve another circuit by applying Thevenin's theorem, so it will be more clear. Now in this network, what we want to find out is, we want to find out how much current is flowing through 2 ohm resistor using Thevenin's theorem. So this is the 2 ohm resistor through which we want to find out the current value. Now in the first step, what we have to do, again we will remove that 2 ohm resistor or the concerned resistor, and these are the two terminals between which this load resistor is connected. So now after disconnecting or after removing the load resistor, the circuit will look like this. These are the two terminals A, B. Now between these two terminals, these open terminals, the voltage, how much will be dropped, that will be the measurement of VOC or VTH. So we have to simplify this circuit to find out this value VOC. Now there may be again many methods or many rules to simplify this circuit to find out VOC value. We will apply that method which will be more efficient. Now as we can see, if we analyze the left side of this network, then we can see here these three components are connected in series and they are forming a loop. So we can easily apply a KVL here, and if we come to the right side of the circuit, we can see these three components are connected in parallel. So we can easily apply KCL here to find out the VOC value finally. Now another way to simplify this circuit is, in the left side what we can see is these three components are connected in series and there is a single voltage source, two resistors. So we can easily apply voltage division rule here to get the voltage drop across this 5 ohm resistance. Now what we can see here, that these two resistances are having the same value. So the voltage what will be dropped across this 5 ohm resistor will be just half of the value of this voltage source. So that is 6 volt. So it will be 3 volt. Again, if we apply the voltage division rule, then that will also give us the same value. So it will be 5, this resistance value, divided by the summation of both the resistances. So 5 plus 5 into 6. So it will be again 3 volt. Now in the right side of this network, what we can see here, that since these two resistors are connected in parallel, so here the current, how much is flowing from this current source, that will be divided into two parts at this point, and separately they will be flowing through this individual resistor. Now again, these two resistors which are connected in parallel, they are having the same value. So what we can say here, that the half of the currents of this current source will be flowing through this 3 ohm resistor. So here the current value which will be flowing through this resistor, it will be simply half of the main current of this current source. So it will be 2 ampere, as both the resistors are having the same value. And if we go by the current division rule at this point, then that also give us the same result. So it will be the opposite resistance, means this 3 ohm divided by the summation of both the resistances, so 3 plus 3, and then the main current value which is 4. So it will be again, this will give you half, so it will be 2 ampere. So 2 ampere current is flowing through this resistor, and that is flowing in this direction. So when a voltage will be dropped, when this current will be flowing through this resistor, a voltage will be dropped, and current since flows from higher potential to lower potential, so this will be positive terminal, this will be negative terminal. So the voltage drop across this 3 ohm, it will be the main current that is flowing through this resistor, that is 2 ampere multiplied by the resistance value, so it will be 6 volt. For this resistor, the voltage drop that we have obtained, this will be at higher potential, this will be at lower potential. As for this part of the circuit, this voltage source, the current it will supply, it will flow in the clockwise direction. So through this resistor, current will be flowing from higher potential to lower potential, and with that logic we can say this will be plus, this will be minus. Now if we mark this point as C and these 2 points or terminal are same, so we can say that VAC that we have already obtained as 3 volts, so VAC will be 3 volt, and VBC that now we have obtained as 6 volt, so this is 6 volt, and VOC will be VAC plus VCB. Now VAC is 3 volt and VCB is minus 6 volt. As VBC is 6 volt, so VCB will be minus 6. So this value will be minus 3 volt. And if we apply KVL in this path, then also we can easily find out the value of VOC by the help of these two values. So what we can here conclude that in the original circuit, the current which we assumed as flowing from terminal A to terminal B in this direction from left to right through this 2 ohm resistor, actually through this resistor the current will be flowing in the opposite direction, because with respect to that assumption of the direction, the polarity of this voltage value VOC we took as this positive and this is as negative, and finally the VOC value that we are getting as minus 3 volt. That means actually the polarity of this voltage VOC will be, this will be at higher potential and this will be at lower potential. Now in the next step what we will do is we will find out the equivalent resistance of this circuit when we will look from these terminals. So this is our A and this is our B, between which this 2 ohm resistor was connected, and now we will look into the circuit from this side. Now if we look that way, then we can see here that these two resistors are connected in parallel, so easily we can find out the equivalent resistance value of this parallel connection by applying that formula or concept. Now here we can see that these two resistances are having the same value. That means the equivalent resistance, if we take that as R1, then it will be half of their each value, which is 5 ohm, so it will be 2.5 ohm. And also if we look at the right side of this circuit, here also we have a parallel connection between these two resistors, so again by applying the formula we can easily find out the value. But again here the two resistors are having the same resistances, so here also the equivalent resistance value will be half of their each value, so it is 3 ohm. That means equivalent resistance will be 1.5 ohm. That means between these two terminals AB, in the modified circuit, we will have only two resistors. Between this point and this point, we will have this R1 having value 2.5 ohm, and between B and this point, we will having this resistor having value 1.5 ohm. That means between A and B, these two resistors finally will be connected in series, and their equivalent resistance, which will be called as RTH, Thevenin's equivalent resistance, that value will be 2.5 plus 1.5, so it will be 4 ohm. Now in the final circuit we will have this VTH or VOC, and with that this RTH will be connected in series. This VTH has value minus 3 volt that we have already obtained, and this RTH has value 4 ohm that also we have obtained. And what we will do next is we will reconnect the concerned resistor through which we wanted to find out the current value, and that value was 2 ohm. Now as we can see here, all these three components are connected in series, so finally the current value will be VTH, which is minus 3 volt divided by RTH plus RL, 4 plus 2, so it will be minus 0.5 ampere. Now as per our assumption, current was flowing from left to right from A terminal to B terminal, and that value is minus 0.5 ampere. And as I already said, actually the current is flowing opposite to our assumption. So current is actually flowing from B to A, and that current value will be positive, and that will be plus 0.5 ampere. So this is the way how we can apply Thevenin's theorem in electrical network to simplify that and to find out the desired parameter. Now this class was about a DC network where we have only independent sources. Now in the next class I will discuss about how to apply Thevenin's theorem in DC network where we may have dependent sources along with independent sources. So with this I end today's class. Thank you.